Okay.
Yes.
Okay.
Okay, good morning, everybody. Good morning for me. Good time for everybody. And this is the session of machine learning with and for software engineering, number 3. And we have a lot of papers in this session. So we have 7 papers, very interesting session. So I remind you that you have only 5 minutes. So please forgive me if I stop you after 5 minutes. So we will start with the first paper that is a journal first and is in HIDE, Code Generation from Natural Language, Promise and Challenges from Frank School, Bogdan Vasilescu, Graham Neubik, and the presenter will not join us for the time zone. So our chair, Manuel, will share the video. Enjoy the video.
Yeah, I guess I am having some issues with the presentation, so if we can skip and then I'll play
Okay, we will
the video.
skip. So we go. Yeah, thanks. Okay, we
Okay.
go to the second. So we move at the end. Okay, Manuel, the last
Yeah.
presentation.
Okay.
Okay, so we move to the second presentation that is active learning on discriminative subgraph patterns for API misuse. Oh, sorry, I don't have the full name. Okay. So active learning of discriminating subgraph patterns for API misuse detection. This is a paper from Journal First and Track, and is on Ong Jin Kang and David Lowe. No, actually, there is something. Okay, David Lowe, yes. So we have Ong Jin Kang that will present the paper. Thanks,
Okay.
please.
Should I start? Thanks for the introduction. So I'll start talking about our work. So the context of our work is that modern software systems rely heavily on third-party libraries. And for a client program to interact with these libraries, they do so through the APIs that are exposed by the libraries. However, APIs may have usage constraints associated with them, and the violations of these usage constraints are known as API misuses. And API misuses may lead to bugs and vulnerabilities, and therefore it is important to detect them. So in prior work, it has been suggested that we could mine frequent patterns from projects on GitHub, and this was promising, and they had very good improvements. And an example of a frequent pattern is shown on the right here. And this frequent pattern encodes the need for a null check on the return value of map.get. So given this pattern, we could detect misuses by looking for deviations from them. However, in this paper, we argue that GitHub alone is an unreliable teacher because frequency isn't equals to correctness. The first reason is that there are many wrong examples of APIs on GitHub. So if we try to learn from these examples, we would learn misuses instead. And also, frequent patterns may not represent usage constraints. For example, it is frequent to see print lines together with a map.get, but that does not mean that we have to print line every time we retrieve something from a map. So in this work, we try to overcome this problem by transforming the task into a supervised machine learning task. And we involve a human annotator for supervision. So a human annotator would label if an example from GitHub is a misuse or is a correct usage. And given with the labels on the examples, we can then mine discriminative subgraph patterns, which in contrast from previous work, which mines frequent patterns. Discriminative subgraph patterns are patterns whose absence or presence would be indicative of a graph class, in this case, whether it's a misuse or a correct usage. However, human labeling requires substantial human effort, and we cannot expect a human to label every example on GitHub. And so we look to the field of active learning, which aims to query humans of labels of only informative and representative examples. Within our work, we take the following interpretation of representativeness. So the idea here is that we want to label only a small number of usage examples such that we can learn something about some patterns that is sufficient to characterize many examples from GitHub. And then this would give us, this would allow us to figure out which examples should a human labeler annotate. And then after we've identified the discriminative subgraph pattern, the goal is then to try to classify examples at test time. So to do that, we want to construct a vector that can be passed to a machine learning classifier. So to do that, we would first take the test example program and convert it into a graph. And then we would enumerate over the discriminative subgraph patterns to see if the subgraph matches the graph or not. If it does not match, then the vector will be filled with 0 at that corresponding element. And if it is a subgraph of the then we fill it with 1. So we do this for all the discriminative subgraph patterns. And this gives us a vector of 1s and 0s, indicating if the discriminative subgraph pattern matches the test program or not. And then afterwards, this would mean that we have a vector that we can pass to a classifier. So initially, we would train the classifier using the vectors from the training data set. And then afterwards, we will be able to use the classifier at test time. In total, we studied about 57 APIs, including APIs from both the standard libraries as well as common third-party libraries. So we collected examples from GitHub. An average of over 2,300 examples were labeled. And on average, we had to label about 50 examples. And then afterwards, we evaluated our work that we term ELP on MuleBench, which is a standard benchmark for detecting API misusers. And then we find that we outperform the previous approach, MuleDetectXP. So in the first half of this table, we see examples that mine patterns from Moonly within a single project. And then subsequently, MuleDetectXP mine projects and examples from GitHub, and they had a lot substantial improvements. And then using active learning, we see that outperform MuleDetectXP. So in summary, we looked at the problem of API misuse detection. And then while finding patterns from projects across GitHub was promising, GitHub alone may not have been a good teacher. In our work, we use active learning to direct human attention to informative and representative examples. And then we select the examples for a human annotator to label. So that's all from me. Thank you for your time.
Thanks a lot. Thanks a lot. You were in time.
Yes.
And we move the question at the end. So we go for the third presentation. Thanks a lot again. That is the presentation of paper with title Dependency Tracking for Risk Mitigation in Machine Learning Systems. The speaker is Sherry Xu, and the work is joined with Limin Zhu, Qinguan Lu, and Chen Wang, and Zhen Wang. Please. We cannot hear you. Sherry, can you switch on the microphone, please? We can see the slides, but we cannot hear you. The microphone is switched off. You have the bottom on the left side of the screen. Manu, can we help the speaker to switch on the microphone?
Okay, sorry about it, everyone. Let me share again. I'm trying to figure out how to close the.
Yes, don't worry.
Yeah.
Okay.
Okay, I share my. I probably need to. Sorry about the delay. Probably need to open my slides again. Okay, I got my slides opened. Now I share my window again. Can you see my slides?
Yes.
Okay, so I'll start straight away. So the problem we try to target in this paper is the data-dependent behavior of machine learning systems, which may cause the risks. And dealing with such risks in the development phase needs non-trivial costs due to the uncontrollable data generation processes in the test phase. So continuous monitoring and validation at runtime is a more realistic and cost-effective way for machine learning systems. However, there is a gap between the model algorithm level solutions and uncertainty handling at the operational level. So in this short paper, we propose a risk management system for machine learning systems that cover the machine learning pipelines at both the development stage and the system that use the generated model at operation stage. And objectives of our paper is firstly to manage the complex relationship between dataset models and the predictions and the associated explanations. Secondly is to support immutability, as there are multiple parties involved at operation time. And lastly is to identify uncertainties by tracking explanation consistency. Here is the overview of the architecture we proposed in the short paper. From data management perspectives, the raw data sets are normally contributed by multiple stakeholders. There could be a dataset registry that maintain a list of existing datasets. And it's good to have a version control tool to track the evolution of the datasets. The model management components are similar to the data management components in that there could be a model registry that maintains all the existing models. The model with large size could be stored in a separate model database because model is also data. And similarly, a version control tool like GitHub could be used to manage and maintain the source code of the models. As query management, our architecture capture the dependencies among queries or predictions with models and the corresponding data sets. So we are aim to provide monitoring mechanism which is triggered by the queries from the end users of the machine learning systems. The parties which who submitted the queries may got different answers at 2 different times from a single prediction model. Any change to the underlying data could cause this consistency. We use a blockchain to provide an immutable and publicly accessible data infrastructure to store the provenance data about the dependencies among query model and data sets. And we use a graph database to store and visualize the provenance data stored on a blockchain infrastructure. And a provenance injector keep monitoring the event of provenance data being added to the blockchain. And whenever the provenance data is updated on blockchain, the graph database is updated accordingly. Okay, conclusion. This paper tried to deal with the risk due to the data-driven nature of machine learning systems, because those risks are difficult to mitigate in the development phase alone. So we propose a dependency tracking system in the paper, which is aimed to manage the risks across development time and operation time of machine learning systems. And we try to achieve transparency and explainability by using use blockchain to provide a publicly accessible data infrastructure to store the provenance data, and also use a graph graph database to visualize the provenance data and the dependency between prediction result model and data sets. Thank you, everyone.
Okay, thanks a lot. We move for the next presentation. The paper is title is DeepFT, Automated Fault Diagnosis and Localization for Deep Learning. The paper, sorry.
Sorry.
Julian Cao. So please, can you hear us?
Yes, I can hear you. Can you hear me clearly?
Yes.
Okay, thank you. So I will start.
Yes, please.
Okay. So hello everyone. It is my great honor to introduce our work, DeepFT, Automatic Fault Diagnosis and Localization for Deep Learning Programs to all of you. Before I start, I would like to introduce the cooperators from 5 institutions. It is a great honor to work with you. So let's get started. As deep learning systems are widely used in our daily life, how to automatically debug such systems become essential. So our work is designed for debugging DL systems. It is a learning-based fault diagnosis and localization framework. And by saying learning-based, it is because we regard the fault diagnosis problem as a multi-label classification problem. It learns to distinguish the normal and buggy DL models according to their runtime features. It goes beyond the bug detection. It can also diagnose the root cause of a fault and pinpoint the faulty lines in the program. The secret of DeepFT is that some runtime information exhibits significant correlations with certain types of faults. For example, the figure shows the distributions of several features when the learning rate and loss function are faulty, painted in red, or not faulty in blue. We can observe that there are obvious statistical differences when the learning rate and loss function are set appropriately or not. This observation enables us to perform fault diagnosis and localization as a learning problem while leveraging the relevant stochastic runtime information of a buggy DL program. Based on this idea, we then zoom out to a bigger view. Here is the whole picture of DeepFT. The upper part is the workflow of DeepFT, while the lower part is the preparation for it. We will skip the details of the lower part and briefly introduce the upper part. The workflow of DeepFT comprises 3 steps. Given a program, DeepFT constructs the DNN architecture and collects runtime data such as loss and neurons information by training the DNN model. And after applying a series of statistic operators, the diagnosed features are produced. Then we infer the possible types of faults using the pre-trained diagnosed models prepared by the lower part in the previous slide. And since there are usually more than one faults in the program, so we adopt a multi-label classification model so that one buggy program could be assigned to more than one fault type. Finally, DeepFT goes through the nodes of the parsed abstract syntax tree, traverses assignments and expressions, and identifies the lines where the diagnosed types of faults are defined. Note that currently the diagnosed models are trained to classify 5 major types of faults, including unsuitable loss function, optimal activation function, insufficient training iteration, and inappropriate learning rate. We made it extensible for supporting more types of faults. We also constructed a benchmark with 58 buggy programs from Stack Overflow and GitHub. The benchmark includes the fault programs, the patches, usually more than one, the types of faults, and line numbers where the faults are introduced. The left-hand side shows the number of each type of faults in the benchmark. As highlighted in yellow, we can see that the top 5 types of faults account for more than 70% cases. This is the reason why our current DeepFT are designed to debug these 5 types of faults. In addition, we further present the statistics of the number of fault types in blue and the number of faulty lines in red. We can see that over half of a program contains more than one fault types, and most of them involve more than one line. And this observation motivates us to adopt multi-label classification algorithms. In conclusion, DeepFD maps the fault localization task on DL programs to a learning problem. We also constructed a benchmark for future fault localization works, and the work encapsulates the fault seeding, fault program checking, feature extraction, fault diagnosis and localization, and it has been made online available. That's all for this presentation. Thanks for listening. All questions and cooperations are welcomed. We are glad to hear from you.
Okay, thanks a lot. Very interesting work. And we move ahead with the next paper, that is what do they capture? A structural analysis of pre-trained language models for source code. The speaker is Wow Wan, and the paper is the other speakers are Hongyu Zhang, Haijin, Yelin Sui, Wei Zhou, Kangor Xu. Sorry for the pronunciation. Please.
Okay, thanks for your introduction. So could you share screen now?
Yes.
Okay, then I will start. Hello, everyone. This is Yao Wan from the Huazhong University of Science and Technology, China. Today, I will present our work titled, What do they capture? A structural analysis of pre-trained language models for source code. This work is joint with some collaborators from the University of Newcastle, University of Technology, Sydney. You know, with the development of artificial intelligence, various work have been proposed to apply machine learning techniques into automating the several code-related tasks, such as code classification and code summarization. In the code intelligence tasks, one fundamental task is the code representation learning, which aims to encode the source code semantics into distributed vectors. The learned code embedding can support various downstream tasks, such as code classification and code summarization. And recently, pre-trained language models of source code, which are based on self-supervised learning, have attracted much attention, such as the CodeBERT, GraphCodeBERT, PLBART, and many another pre-trained language models for source code. However, the pre-trained language models for source code are always very large and very complex, always considered as a black box. And from our investigation, we can say that current studies only explore in which scenario does the model works, and it is still not clear why this model works and what future correlations they can capture. So it motivates us to our work. In our work, we aim to open the black box of pre-trained language models for source code. In particular, we aim to answer the following questions. Can the existing pre-trained language models learn the syntactical structure of source code written in programming languages? To answer this question, we propose three sub-research questions. The first research question is, does attention align with the structure of source code? To answer this research question, we propose an attention analysis. You know that the pre-trained language model are always composed of a series of transformer layers, which is always based on the self-attention mechanism. So in this research question, our clear insight is that if two nodes in AST are close, their attention will expect to be close. For example, given the code on this AST, we can see that the leaf nodes sys and exist are very close since they share one parent. So we think that their attention between them should be high. So we introduce a proportion of high attention token pairs as in this equation, where the alpha ij denotes the attention from S token to JS token, and the FWI and WJ returns 1 if WI and WJ are in a syntax relation. So using this equation, we can verify the connection between the attention and the syntax structure of source code. Our empirical results reveal that the attention actually aligns strongly with the syntax structure in AST. It's purely in the deep layers. Our second research question is that can pre-trained models embedded the syntax structure in its contextual order embedding? In this research question, we propose order probing approach. The key insight is that the tree structure is embedded if in the transform space, the distance between two words vectors should correspond to the path length between the words in syntax tree. For example, given an AST, the path length between the function define and the define nodes are 1, and the path length between the load in and for is 2. So we first map the original order embeddings of in and load in and for into a transform space using a matrix B. And in the transform space, our assumption is that the distance between them should also be close to 2. So based on this insight, we can learn the matrix B in a supervised learning way. And in this research question, our experiments show that the syntax structure of source code have been well preserved in different hidden layers of the pre-trained language models. And also, our third question is that are pre-trained models able to induce the syntax structure of code? We aim to induce a syntax structure of source code based on its order embeddings. Our insight is that if the distance between these two words are close, they are expected to be syntax tree.
Sorry,
okay, I'll quickly do this.
Sorry.
Okay, maybe 1 minute. Okay, sorry. Our insight is that if, for example, if list the vectors of OPT and meta similar, so they are also be expected to be close in the AST. So that based on this insight, we propose a greedy top-down inference algorithm based on the recursive partitioner algorithm. Okay, this is also a case study. So our experiments show that the pre-trained model can learn some syntax structures of source code. Yeah. Okay. Thank you. Sorry for my.
Thanks a lot.
So,
thanks. So we move ahead to the next presentation for the paper, a universal data augmentation approach for fault localization. The speaker will be Wang Xi, and the paper is a joint work with Xing Qian, Yu Yanlei, Meng Yang, Xiongkang Mao. Please.
Yeah. Can you see my screen?
Yes.
Okay. Let me start. Hello everyone. It's really a good honor to be here to introduce our work. Today, I'm going to share our work, a universal data augmentation approach for fault localization. Software bugs are prevalent in modern software systems, and software debugging requires a significant level of time for developers. To reduce the cost, researchers have proposed various fault localization techniques during the past several decades. Fault localization techniques provide automated ways to assist developers in locating buggy lines. Two kinds of classical fault localization techniques are spectrum-based fault localization and deep learning-based fault localization. The general pipeline of SFL and the DLFL technique is shown as follows. The raw data are collected from runtime information when the buggy program is executing the test cases in the test suite. Spectrum-based fault localization technique use formulas and deep learning based fault localization use neural networks to evaluate the suspiciousness of each program entity. From the above pipeline, we can observe that the effectiveness of SFL and DLFL heavily relies on the quality of the input raw data. But the quality of the raw data poses severe threats due to the class imbalanced test suite in real-world programs. First, the following test cases only takes up a small proportion of all test cases, which means we face a between-class imbalance problem in the real-world test suite. The second, real-world programs are large in size, but only several lines of code or even one statement is responsible for program failure, which makes it harder to capture the buggy lines. So the effectiveness of many SFL and DLFL techniques are limited by the input raw data. So we propose a data augmentation approach, ANIS, which generates synthesized following test cases from reduced feature space for more precise fault localization. Our approach focuses on the raw data rather than the test case in the original test suite or the fault localization algorithms. Our approach includes two stages, namely dimensionality reduction and data synthesis. The first stage is dimensionality reduction, which takes the raw data as input, filters out the potential bug in relevant statements, and then outputs reduced data. For this purpose, we use the feature selection algorithm, where the following data synthesis stage will construct a generative model for the program. After the model is well trained, it can generate data until the class is balanced. That is, the number of following test cases is equal to that of passing test cases. In detail, we use conditional variational autoencoder for data synthesis. The data synthesis stage has two main steps, the training step and the generating step. For the training step, the conditional variational autoencoder models combines input data and the latent variable with labels. The training steps will build a model which can sample new data through the underlying probability distribution. The generating step will use the decoder part of the model, and the conditional vector is set to 1, 0, 0, 1, representing the following test case. Therefore, we can synthesize following test cases until the test suite is class imbalanced. Finally, ANIS takes training data and generated data as a whole for the next fault localization techniques. For example, SFL or DLFL. In summary, we propose a data augmentation approach, ANIS for fault localization. The key ideas of ANIS are treating coverage metrics and failure vector as samples and labels. And we reformulate the test case generation problem as a data augmentation problem. We tackle the high-dimensional and class imbalance problem by feature selection and data synthesis. We implemented our idea and evaluate ANIS on real-world datasets. And that's all for my presentation. Thank you.
Thanks a lot. Very, very interesting work. And we move to the sixth presentation. The title is Deep State, Selecting Test Suite to Enhance the Robustness of Current Neural Network. It is a paper from the technical track, and the speaker is Zixi Liu. It's a joint work with Yanfeng Jingying and Zhenyu Chen. Please.
Thanks for the introduction. Hello, everyone. I'm honored to be able to participate in the IXC meeting. Today, the title of my presentation is Deep State, Selecting Test Suites to Enhance the Robustness of Recurrent Neural Networks. I am one of the authors of this paper, Zixi Liu. I'm from Nanjing University in China. Below, I will officially start introducing our paper. In this paper, we proposed a test data selection tool for recurrent neural networks. As we all know, deep neural networks have been widely adopted in many fields, but there are still many errors in real-world application scenarios. In this work, we focus on the analysis of RNN, which is a special kind of DNN. With the RNN unfolded, each neuron in RNN's hidden layer updates its state and weight iteratively over time steps. Due to the differences in working nature and the network structures between RNN and FNN, many existing testing criteria for FNN is not applicable for RNN. Now, let me summarize the challenges we are trying to solve. The first is why we need to select test data. Because the testing and optimization of RNN models rely on label data, and the cost of collecting and labeling data from real applications is high. On the other hand, the existing test case selection techniques are rarely applicable to RNN models, and the analysis methods of RNN models often aimed at the advertiser sample detection, which may have limitations in real-world applications. This figure is an overall process of deep state. It first unfolds the RNN model according to the time steps and captures the predicted label sequence based on a stateful view. Then, deep state calculates the changing rate and the changing trend. These metrics are employed to evaluate the uncertainty and the internal state transition of the RNN when processing the input data. Finally, we apply deep state to select a subset of data from a large unlabeled dataset for RNN models. Now, let me show some experiments in our paper. We experiment deep state with image classification and text classification models. For each data type, we employ 2 widely used datasets, and we apply some data mutation operators to simulate the data collected from real applications. This is the bug detection rate of different selection methods. As can be seen, in each combination of dataset and model, the test set selected by deep state has the highest bug detection rate. And this is the bug detection rate of 10% and 20% selected tests. Similar to the results shown in the graph on the previous page, deep state has the highest bug detection rate for each selection ratio. In this page, the x-axis of each line chart represents the selection ratio from the candidate dataset, and the y-axis represents the inclusiveness of the selected dataset. With the selection ratio increasing, the inclusiveness of the dataset selected by all methods is improved. Among them, deep state outperforms other selection methods, which indicates that deep state can select more bug test cases under the same selection proportion. In this slide, we show the RNN's accuracy score on test datasets after retraining with 50% selected tests. As can be seen from this table, in all models and datasets, compared to random selecting data for retraining, the data selected by deep state can generally improve the accuracy of the RNN models. That's all for my presentation, and thank you for your listening.
Thanks a lot. And while we recover the first presentation, because we have a video, I would ask to the authors to have a look to the chat. There are 3 questions, some questions, 2 for Sherry and 1 for Yao. So you can be prepared for the discussion.
Okay.
Okay.
I guess to share the screen to play the
please.
video.
Yeah.
Okay.
So the next presentation is a video recorded. Okay. In eDecode generation from natural language. Go, please.
The version is at arXiv. And we propose 3 research questions. The first being, how does using a natural language code developer assistant affect task completion time and program connectedness? And the second being, how do users query the natural language code assistant, and how does that associate with their choice of generated versus retrieved code? And the third is, how do users perceive the usefulness of the in-ID natural language code generation assistant? For this, we designed a user study. To facilitate the user study, we first developed a plugin for the PyCharm IDE that implements a hybrid of code generation and code retrieval functionality. Both of these are based on the previous state-of-the-art models and conventions. Then we orchestrate virtual environments to enable collection of many user events, for example, web browsing keystrokes and fine-grained code edits. To test the users, we have to design several tasks that are using Python programming languages. We designed a total of 7 varieties of Python, 14 Python programming tasks ranging from like basic file manipulation to machine learning, data visualization. And we asked the developers with various backgrounds, demographics to complete some of these tasks randomly with or without the help of the plugin. And finally, we collect the data, analyze them, and try to answer the questions we proposed. So, to answer the first question, how does using a natural language to code developer assistant affect task completion time and program correctness? Surprisingly, program correctness and task completion time are unaffected. The results are inconclusive and insignificant in terms of the difference between using and not using the plugin. To calculate the program correctness, we scored them using a semi-automatically process following a predefined rubrics. Here is the distribution of the task completion time. We can see that for those with many data points, the difference is negligible. And this is the distribution of the task correctness score ranging from 10 to 0 to 10, which follows the same trend. And the next question is, how do users query the natural language code assistant, and how does that associate with their choice of generated versus retrieved code? Here's an example where we train a simple bag-of-word logistic regression classifier of the user's natural language queries and how what kind of generation or retrieval snippets they end up selecting. And here are the top 20 features. And from here we can see that, for example, the generation models seems to be good at generating simpler tasks, for example, like open, read file, date, time, and dictionary, text file, and all that kind of stuff. On the contrast, for the retrieval based models to work better, they usually deal great with those machine learning, data analysis, or data visualization problem, as we can see here, like matplotlib, data frame, sklearn, cross-validation. Another sub-question is, how well specified are these queries? Here is a confusion matrix of how good the query is on its own, or how good the query is with the context, like user context code, and how they end up being generation or being retrieval. And from this, we can see that like natural language queries analyzed are more often than not insufficiently well specified for even the human expert to be able to write code implementing those intents. Like we can also see that moderately high and statistically significant association between the success of the code generation model. That is to say, the study participants choosing one of those candidate code snippets and the quality of queries. And then we also noted that the input query quality can have a big impact on the performance of the code. The final research question is, how do users perceive the usefulness of the IDE Natural Language Code Developer Assistant? They are twofold. The good thing is that they feel that the plugin helps find code snippets the developer is aware of but cannot fully remember. And the second is, using an IDE plugin is less disruptive than using a web browser. However, there are many aspects that can be improved. For example, the quality of code generation and retrieval result could just be a little bit higher. and the users could benefit from additional context. The plugin could benefit from additional context as well, and querying the plugin could be interactive.
Okay.
Thanks, Manuel. So we have 50 minutes for discussion. We have very interesting question on the chat. And I don't know, maybe to one has been, there is the answer there. But mainly there is a question for Sherry Xingwei about the learning overhead of the approach for data scientists. Yeah, and also, please.
Yeah, sure. The question, first, thank you for the very interesting question, which make largely a lot of sense to me. I guess I probably could explain it in another way, that our work is initially try to extend existing open data platform, which is data.gov.au. That is a government open data platform. We are trying to extend the functionality of the current data platform to support like sharing data analytics models. And I guess in this context, the version control tools are mainly used by the data providers of the data platform, which in our case is the government agencies rather than the data scientists that use the open data. And I think the second, I hope I answered the question. And I see the second question is also to me. The question is, how does the immutable provenance implemented take into account the access of different stakeholders to data? I'm thinking of, for example, in a bank where getting access to data is extremely difficult because they are required by law to implement the proper permission and access rights, which I agree. And as I mentioned earlier, that this piece of work is initially targeted more platform rather than the scenario mentioned by Luis. I hope I pronounced your name correctly. But if we would like to apply similar, I guess, data sharing platform among among stakeholders with more sensitive data, then it probably doesn't work.
Yeah, this is a big problem. It's also
it's a challenge. Yeah. But thank you for the questions. Yeah.
Okay, thanks. So I move ahead to Yao. Yeah. Luis, I don't know if you want to
okay. Sorry. I just see the question now, but I need some time to think about it. Okay. So I will answer for next one. Okay.
Okay, so again, there is another question about the training data, where they come from, to Jalun on the chat. But
yes,
yeah,
I answered it.
Yeah, probably you answer on the
Chat.
right?
Yes.
I don't know if Luis is okay with the answer, or you need more explanation.
Well, actually, the process of preparing the training data and to train the diagnostic models are a very complicated process. So, as briefly speaking, we seed faults in the normal programs, and then we later on collect the runtime data, and then we label them. So there are basically 3 steps to prepare those models, and you may refer to the section 3.2 in our paper for more details.
Okay, Luis. Okay. So there is also, yes, I don't know if somebody.
Hi, Luis. I think I can try to answer your question now. Yeah, you think that is there any syntax structure pattern yield the consistent attention weights? Yeah, actually, I think maybe there may be some structure patterns that yield are consistent to the attention weights, but in our approach, we try to think in an operator way. We try to observe some interesting findings from the attention weights. So, but we haven't considered there are some bad case that are not consistent with the attention weights. I think maybe it's interesting future direction to explain.
I was asking this because it's usually. Do you hear an echo, by the way?
Yeah. Can you?
Yeah, I can hear you.
I was asking this because it's usually quite interesting to look at the exceptions to our rule. Yeah. So you came up with this answer that usually attention weights are consistent. I was wondering if in some particular cases this wouldn't be the case, and if you were discussing it somehow. But nevertheless, it's great work. So thanks a lot.
Yes. Okay. Thank you. I think we'll try to explore some bad examples for the attention analysis. Yeah. Thanks for your suggestion.
Okay, thanks. And I have a question for Hongjin Kang about the detection of misuse of API. And my question is, if I understand well, you applied this on the code, so mainly, so doing the analysis of the code. I don't know if we can apply or how we can apply the approach looking at the traces in order to detect misuse of API during runtime. Yeah.
Right. So thanks for the good question. So frankly speaking, this was something I was thinking of a lot when I wrote the paper and even now. So the answer is very broadly yes, but there would be the usual trade-offs between static and dynamic analysis. So of the static analysis, we compute a graph that has a lot of information and would capture all the possible executions. But on dynamic analysis, we would only capture one execution trace. So that could be a problem that could cause it to miss some patterns. But it is certainly possible that generally the entire approach of taking code from GitHub and then executing them and then obtaining the execution traces, then we could mine patterns from those execution traces. And the usual ideas in my paper could be applied there, where we could ask a human annotator to label the examples, and we could mine sequential patterns from the execution traces. Yeah, so that
maybe
I guess in principle, yes.
Yeah, maybe if you can have some pattern of misuse, you can at least try while the execution is going to find if the execution trace goes in that pattern. So maybe you can rise before that the misuse happen. I don't know, maybe.
Yeah.
I think
that would be similar to runtime verification, I guess. Yeah.
Yeah, somehow. Yeah.
Yeah.
Okay. Thanks a lot. Very interesting paper. I mean, this session is very interesting. I mean, a lot of novel ideas and novel contribution. There is any other question from the attendees, participants to the session? Any other comments? Also, authors can ask to each other if they have some comments or something to ask. Okay, so I will try to, I have another, let's say, comment or a discussion to arise that is about the quality of machine learning, okay? So, for example, we can talk about explainability. I heard a presentation that talked about this, and we can also think about fairness of the approach, because we are using this for social goods, social things now, and every day we know that machine learning is used in several domains. So my question is, which kind of, if your approach can embed the detection or the consideration of some quality in terms of fairness, explainability, interpretability, and other things. Okay, something like that. Please, do you have any idea?
Maybe I start. I think our architecture, although it's a very rough design, could provide accountability of the, I guess, machine learning pipeline that cover both, as I mentioned earlier, cover both the development phase and the operational phase. Other than accountability, we also try to provide some explainability, although the explainability, our explainability is not on the, I guess, the algorithm level, but mainly on the, I guess, provenance data that try to link the query or the prediction with the model, and also the data set used to train the model. Yeah, that's two qualities.
Yeah, and also because explainability can help also the developer to better understand which is the problem, let's say in the code in case of detection or misuse or fault.
Yeah, exactly.
Yeah, so can help a lot.
Yeah.
And we also have to consider the explainability in our work. So in fact, we're using the tree-based models for training the diagnosis models. So we are trying to find the correlations between the runtime features during the model training and the faults in that program. So actually, we are trying to a bit reveal the correlations between features during training and bugs in the program.
Okay, very good. Yes, tree-based models are interpretable, so they can help a lot.
Yes, but it's very hard to explain. When we try to explain that, we find it's difficult.
Yeah, I believe you. Other comments?
Right. So in the case of learning from GitHub in general, I guess the provenance of where the data came from and which code examples from GitHub contributed to the prediction or to the classification, that sort of information would be useful to explain a prediction.
Yeah. Yeah, and this is important.
Yeah.
Yeah, cool. Okay. Any other comments from the other speakers?
Yeah, I have a comments. I think that it currently I think the quality of machine learning techniques are very important and interesting topic in the software engineering community. Actually, there have been many works in the AI community. In the AI community, have trying to explore the quality of machine learning techniques from the robustness, the explainability, and the fairness of the machine learning models. And actually, in the current software engineering community, I have seen some papers on trying to explore the explainability and the robustness of the source code. For example, if we can change some tokens of some variable names of the source code, then the model will not work. So I think the current machine learning models for source code are very so I don't know how to say very weak.
Fragile.
So fragile. Yeah, it's fragile. Yeah. So I think this is also an interesting topic, and we are also trying to have some initial exploration on this topic. And another interesting topic is that the fairness of the machine learning techniques. Actually, it's natural to explore the fairness of the machine learning models in AI community, or in the community of recent era for me. But I think it's hard to transfer the same topic, same problem in the software engineering community. So what does in the software engineering community? So I think it is still an open problem. So I still know how to formulate the fairness problem in software engineering community.
Well, I have sorry for interrupt.
Yeah, that's why I think I have this is all my comments.
So as a follow-up while thinking,